Hello everyone, Professor Dustin here. This video is going to be a solution to the whiteboard escape speed. This is a rather difficult whiteboard which has to do with the universal theory of gravity. Recall that what we have is we have a projectile being launched off of the moon, and we have the mass and radius of the moon as given information. Part A says, if I launch a projectile with an initial velocity of 500 meters per second, how high off the moon will I get? So I'm going to try to add to this picture a little bit. So how high, suggesting that eventually it'll get to a certain point and then fall backwards. So the path will be something like that. And the question is asking for that height, how high off the surface of the moon. So there are other ways we could do this problem. The way that I'm going to do it is using conservation of energy. It's possible to do this with Newton's laws, but I find it to be a lot more difficult. So we are going to try to do it using conservation of energy. So recall conservation of energy is the change in energy is 0. And generally that means that the change in kinetic energy plus the change in the potential energy is also going to be equal to 0. And we can rewrite that further by writing that as the final kinetic energy minus the initial kinetic energy plus final potential energy minus the initial potential energy. So now the challenge is to find out what each one of those things are. Well, the kinetic energies, those are always 1/2 mv squared. So the final kinetic energy is 1/2 mvf squared, and the initial kinetic energy is 1/2 mvi squared. Now, this object is being launched at an initial velocity of 500 meters per second, so we're going to have some initial kinetic energy. But as it gets to the top of its path, where we're trying to find the height, that's the final position, and that velocity is going to be 0. Why is it going to be 0? Well, it's the point where it just goes up and stops. Right at that point right there, that's going to have 0 velocity, so the kinetic energy is going to be 0 as well. So now we need to find the final and initial potential energy. So we might be very tempted to say, oh, potential energy due to gravity is mgh. Of course, g is only on the Earth. We'd have to use g for the moon. We can find that. But actually, mgh only applies for very close to the surface of planetary objects like the Earth or the moon. Here, we are presumably going to be going very far away from the moon at a velocity of 500 meters per second, initial velocity. So we are probably not going to be able to use mgh. We're probably going to have to use universal gravity, the formula of which I write it as U big G, the formula of which is minus G m1 m2 over r, where r is the separation between the masses m1 and m2. And recall that G is just a universal constant, 6.67 times 10 to the negative 11 in SI units. But this is just a potential energy function, so now we can just see what the final potential energy is based on the final position, and the initial potential energy based on the initial position. So U final, the final is going to be when it's at a height h. The two masses, I want the mass of the moon and the mass of the object. I've already called the mass of the object m here, so I'm going to leave that as m. And the distance I want as the distance between the center of the moon and the object. The center of the moon is here, the object is here. This distance h is here. The moon has a radius, so the total distance between the centers of the two objects is the moon's radius plus the height of the object. So I'm going to call that rm plus h. The initial potential energy is going to be the exact same formula. In fact, the top will all be the same, because the masses aren't changing between the initial and final state. But the bottom has to be the initial separation between the two masses. Initially, the object is sitting on the surface of the moon, and so the initial separation is just the radius of the moon. So now we have the initial and final potentials, the initial and final kinetic energy. We are just going to apply conservation of energy. So K final is 0. The K initial is minus 1/2 mvi squared. Final potential is right there, minus g m over r moon plus the height we're looking for, minus the initial potential energy. So minus with that minus sign gets me a plus sign, over rm. And that's all going to be equal to 0. That's our condition for conservation of energy. So now we want to make sure that we have all the things we need and that we know what we're looking for. We're looking for the height above the moon. That's that RH right there. So we're going to be solving for this thing, which is in the denominator of this term. OK, so we can handle that. So we have a 0 over here. Let's move everything over to the other side except for that term. So now we're still trying to isolate this guy. But I noticed that I have a GMM here and a GMM there, along with this 1/2 MVI squared. So what I'm going to do is I'm going to divide both sides by this GMM. So if I do that, that's going to divide this part out. That's going to go to 1. Divide both of these terms by GMM. That's going to make this guy go away. And then I'll have just this term divided by GMM. So
that will leave me with minus.
OK, and now we have a nice simplification, which is that this mv squared here, oh, I forgot a factor of 2 for that guy. I have mv squared divided by 2gmm. These are the same m's, so they are going to cancel. OK, so I still need to isolate this h. Well, first thing I'm going to do, just because I'm on a whiteboard, I'm going to multiply times -1 to make that negative go away. So that's going to make this positive, make this positive, and make this guy negative. So the next thing I want to do is, to isolate h, I clearly need to get rm plus h on the top. And so I can do that by taking the inverse of this. So that's just flipping this. That means I need to take this to the -1. And now isolating h is easy because I just need to move rm over.
And I get my final expression.
And now it's just a question of plugging this into our calculator to get a final answer, which I'll do. OK, it looks like my final answer is 7,700 meters. Or, sorry, 77,000 meters, or 77 kilometers. So that's how far above the moon I will go, 77 kilometers. And that's a pretty big number, which is why I could not have used mgh. Only the universal gravity law, negative gmm over r, would have worked here, because once you get that high, mgh fails. So for part B of this problem, I simply have to calculate the escape speed from the moon. So recall that the escape speed is the initial speed that we would need to have to reach the distance of infinity, so as far away from the object as possible, with 0 velocity. So the intuition behind that is that, OK, if I increase my initial speed, I could maybe get to as far away as possible with a larger velocity. I could still be moving. But the very first time when I'm going to be able to get out of the Earth's gravity, in this case the moon's gravity, that's when my final velocity, I go far enough away so I just leave and then I just stop at that point. Of course, we're talking about infinity, so conceptually that's a little difficult, but that's the mathematical interpretation of that physical situation. So it's the same exact problem: conservation of energy, kinetic and potential energies, changes in kinetic and potential energies. I have my final and my initial kinetic energy is 1/2 mvf squared, 1/2 mvi squared. So now I can put in these two conditions. I don't know what the vi is, but I know the vf now is going to be 0. So now we need to know what the potential energies are. Again, we're going to have to use universal gravity. mgh is clearly not going to work here if we're going infinitely far away from the object. So again, I need negative g mass of the moon times the mass of the object divided by the final position. That's rf. But rf is going to be infinity. So this number is going to be some big number divided by infinity. Doesn't matter how big that number is. Anything divided by infinity is going to be essentially 0. So we're just going to set the final potential energy to be 0. In fact, this is how you define the potential due to gravity, is 0 at infinity when you use this formula. For the initial potential energy, I'm going to have negative gm moon times the mass of the object divided by the initial position. If we're starting at the surface of the moon, then our initial position is just the radius of the moon. So now we can start collecting these four terms into our conservation of energy equation. We only have two terms because most of the other ones vanished. The final kinetic energy and the final potential both vanished. So now we just have the initial kinetic with a minus sign because of that minus sign there. This is the initial potential. There's a minus sign there and a minus sign there makes that positive. And now it's just a matter of solving this equation for the initial velocity. First thing I'm going to do is I'm going to notice that both terms have the mass of the projectile in it, so I can cancel them both out. That's a rather important fact. It means that no matter what the object is, the escape speed from the surface of a planet is going to be the same. So it's going to take the same speed of me throwing a ball than for NASA to launch a spaceship. Of course, it's much harder for NASA to launch a spaceship because it's larger, and so we have to give it more energy, but the speed is going to be the same. So now I'm just going to rearrange this equation to solve for the initial velocity. That's moving this term over here, and now I'm going to multiply times 2, get rid of that negative sign, which I can just do like that. And then, so multiply times 2, and then take a square root. And we get a pretty simple expression in the end, the square root of 2g mass of the moon divided by the radius of the moon. And let me get my calculator out so I can give you a value for that. So my final answer is 2,400 meters per second, which is certainly a pretty significant speed, but of course what we're talking about is escaping the potential of the Earth, getting all the way out to infinity when you just stop, so we would naturally expect this to be a very large speed. So for the last part of this problem, we're going to go, instead of on the moon, we're going to go to the Earth. We're going to launch our projectile with the escape velocity of the moon. So if we had a projectile that we could launch off of the moon out to infinity, take that same cannon device and move it to the Earth, that's the speed we're going to launch it out of. How far away do we go? So again, we expect the projectile to not make it all the way away and to make it some height above the Earth. And we're going to launch it at this speed. Now, I'm not sure if I want to plug in the formula for the escape velocity or the number. The formula is always better, but if things get complicated enough, maybe the speed as a numerical number is going to be a better idea. So again, using conservation of energy, delta K plus delta U is 0, change in kinetic plus a change in potential. I have my initial and final kinetic energies. My initial speed is going to be right here. So I could plug this formula right into there, which I think I will do. So I get some cancellation here with the factor of 2's. But I get g, mass of the projectile, mass of the moon divided by rm. That's my kinetic energy, my initial kinetic energy. And again, my final kinetic energy is going to be kinetic energy right there. Presumably, this gets as far away as possible and just stops before falling again. Final velocity is 0. This thing is 0. Now for the final and initial potential energies, I'm now on the Earth. So I need to have mass of the Earth, mass of the projectile. The final will be radius of the Earth plus h. And the initial potential is going to be g m Earth m divided by the radius of the Earth, because in this formula you have to do the separation between the centers of mass. Center of mass of the Earth is here. The initial center of mass of the projectile is right there. That's the radius of the Earth. So now it's just a matter of collecting these things into the conservation of energy equation. And now I can immediately see the benefit of making this replacement as an equation, because now this equation is going to be extremely simple to solve. I have a g in every term, so I can simply divide everything out by g. I also have a little m in every term. That's the mass of the projectile. This is what we expect. We would expect those masses to also cancel. And then we have to be a little bit careful of the different masses. I have the mass of the moon and the mass of the Earth here, so those are not going to cancel, but at least that is going to be a significant improvement in the situation. All right, so what am I trying to find? I'm trying to find h, so I'm going to move this guy to the other side, I think, and leave those two terms on that side. The next step, as in the first part A of this problem, is to invert this, which means, actually, okay. So the next step of this problem is obviously going to be inverting this equation so that we can get h on top. I think before that, I'll just divide everything by the mass of the Earth. So that means that will cancel this term because me divided by me will just be 1 over re, but I'll get another mass of the Earth here. I think that's going to make this simpler when I go to invert this. And now I'm going to invert this equation. So take this, put it on top, and take this whole thing raised to the -1. And then to get my final answer, I just have to move the radius of the Earth over. If you'll notice, basically this is the total distance from the center of mass of the Earth out to the height. So this is going to be the total distance. I just want to subtract re from that because I only want the height above the Earth. And there is my final answer for the height the object goes above the Earth. So now let me get my calculator, plug some numbers in, see what we get. So my final answer is 311 times 10 to the third meters, which is, of course, 311 kilometers. So what do we know about that number? Well, this was the escape velocity of the moon. So if I shot a projectile with this speed off the moon, it would leave the moon's orbit. It would escape the gravitational pull of the moon. So you'd expect that speed to be pretty high, 2,400. 2,400 from the Earth gets me 311 kilometers off of the Earth. So clearly a very big number. MGH would not have worked here, but not actually that far as comparison to going out to infinity from the moon. All right, great. So this has been a solution to the escape speed whiteboard. I hope it's been helpful. Thank you for watching and watching me get used to this great new whiteboard. And I will see you in class.